So we're going to do plenty of optimisation questions in class, but I did just want to go through a sort of algebraic one, and I think this is surprised me with the new specification, this question. It's a standard sort of technique, but yeah, I thought I'd show it to you. So just to recap optimisation then, what we're trying to do is create equations. That's our first port of call. Basically any equations you can from the information that you get in your question. And then we want to create the function we're going to optimise. So of course optimising is looking for a maximum or a minimum, which we know graphically is the turning point. So there's a minimum there, and obviously upside down would be a maximum. Which means I need a function that I can differentiate to set equal to 0 and test for maximum and minima. That means my final equation, the optimising equation, needs to be in a single variable. So it needs to be something like the volume is equal to a function just in terms of the length, which might be x. So it can't have heights and widths and all sorts of other variables. It has to just have a single variable, which is where these additional equations become so useful, because I can use them to get rid of any additional variables that I might have. Once I've done that, I have to differentiate and I have to use the correct notation. So for a function that is maybe the volume in terms of a length x, my derivative will be dv over dx, and I have to keep that notation correct. And then, what are they actually asking you for? Are they asking you for a length, a volume, an area? Make sure you actually answer the question. You would not believe the number of people who lose 2 of the marks in their question because they don't actually give the value to the thing that the examiner is asking them for. So it's a real word of warning there. So here's our question. Let A be the point on the curve y equals x squared with x coordinate A. Okay, well, just like with everything, I'm going to draw a sketch. So here's y equals x squared. Now, if I've got the x coordinate A, my y coordinate would be a squared, and that might be quite useful to us. So we've got the point A, which is actually a squared. And all of that just came from that sketch there, nothing else. But I've done that first. Next part of the question. Let L be the distance from A to the point P to a half. Okay, new little sketch then. So here's the point to a half. Here's P. And I'm just going to put my A point over here somewhere. A squared. And L is this distance here. Now, to work out the distance between 2 points, we go back to our coordinate geometry and we know we need to use Pythagoras. Excuse me. It then says, part A, write down an expression for L squared in terms of A. Well, that just confirms our suspicion that we're going to use Pythagoras, and I just don't have to apply the square root at the end, which is great. So let's work out the height and the width of this triangle. So the height is a squared minus a half, and the width is a minus 2. So L squared then, the long side squared is a squared minus a half squared plus a minus 2. My pen went on strike there. There we go. A minus 2 squared. Okay, sorting all my algebra out, I'm going to expand these brackets. That gives me a to the 4, a squared times by itself, a to the 4, minus a squared. So I've got a half a and another half a, sorry, half a squared and another half a squared, which is just one whole a squared. And then plus a quarter, and then a sort of standard expansion here. So a squared minus 4a plus 4. Okay, my a squares cancel, and I'm left with a to the 4 minus 4a, and then 4 plus a quarter, which is 17 over 4. So now I've got what my function is. I've done part A. I've written down an expression for L squared in terms of A. Great, done. Part B says, find the minimum possible value of L squared. Minimum possible value of L squared. Okay, so there's those last 2 marks. At some point, I'm going to need to make sure I've worked out what L squared is. But it's a minimum. Now, to find out whether something is a minimum, I'm going to need to differentiate the function, set it equal to 0, and then sort of test on that point. Okay, so my function is a function of L squared in terms of A. So when I differentiate it, which I'm going to do now, I'm going to have d of L squared over dA. So my function is L squared. I'm differentiating L squared with respect to A. And that gives me 4a cubed minus 4. Now don't forget, this is one of those important moments here. As I said a minute ago, you do have to make sure that your derivative is in the correct sort of functions, so it's in the correct variables. So it's no good writing dy by dx here. That doesn't make any sense. Y and x don't appear here at all. Okay, so now we've differentiated, we know a minimum and a maximum, but a minimum occurs when the derivative, which is dL squared over dA, is equal to 0. So that's what we're going to do now. So 0 equals 4a cubed minus 4, and I can solve this for a. So a cubed is equal to 1, in which case a is 1. 2 things haven't happened yet. I haven't proven that it's a minimum. All I have is a turning point, and I also don't have the value of L squared. So I need to do both of those things now. So proving that it's a minimum, I need to test. And we know that our test is the second derivative. So I now need to do d2L squared, second derivative of L squared, with respect to A again. That would give me 12a squared. So I'm just looking at this function here and differentiating that again. So now I know that what I'm doing is testing when a is 1, because I think this is my turning point value. So when a is 1, the second derivative, oh, that's an L, is 12. 12 is greater than 0, therefore I have a minimum. Good. So my value of L squared can be found by substituting a into the function for L squared. So this one at the top of the screen here. So 1 to the power of 4 minus 4, lots of 1, and add 17 over 4. And that gives me a value of 5 over 4. That will be the minimum value for L squared. Now this is that second sort of crucial moment here. These are those 2 marks that you're not to lose by failing to read the question properly. We weren't asked for the value of A, though that's been important and pivotal for us. We weren't asked for that, we were asked for the value of L squared. So I've done that there at the bottom. Okay, last but not least, we need to write down the coordinates of the point on the curve y equals a squared, which is closest. Well, we know that the closest point produces the minimum value of L squared, so it must be when a is 1, and we knew that that point was a squared. When a is 1, we get the point 1, 1. And that's it, we're done.